Okay, so yeah, thanks, Gordon, for being here remotely. Very much appreciated that you kind of squeezed it in. And yeah, so we are going to have our final talk of this morning session. Is Gordon Wetzstein. I think doesn't need a big introduction. We all know his massive work, lots of awards, lots of fellowships. Afterwards, we're going to have a panel discussion here with Andrea, and Björn will come back, and Andrew will also come in a little bit later. So yeah, after this talk, feel free to stay here as well and join in the panel discussion. Yeah. So, and with this, I'm handing over to Gordon. Thanks a lot.
Hey, thank you. Thanks for the introduction. Thanks for organizing the workshop. It's great to be here. I apologize I can't be there in person. We actually have our graduation event today at Stanford, so I'm going to have to put on my Harry Potter dress later and hood my PhD students. So they and their families would be very upset if I weren't there. But I want to tell you a little bit about the generative graphics pipeline. My journey in this space begins a long time ago, about 20 years ago, when I was a sophomore, so second year undergrad student. We didn't have any money then, but I wanted to go to SIGGRAPH. I'm also from the SIGGRAPH and graphics community. And at my very first SIGGRAPH, when I was a student volunteer, to be able to afford to go there, I met this guy, Jim Blinn. He was like a hero in the graphics community. You may have never heard of him, but he sort of invented this graphics pipeline. And I happened to have his book, which was called A Trip Down the Graphics Pipeline, in my backpack. So he signed it for me. And that was like the coolest thing ever at the time. So let me just briefly summarize what the graphics pipeline is, because it's very relevant to the discussion of generative 3D models. So typically you start with some kind of a 3D representation, and in graphics that's usually either meshes, a volume, implicit functions, or some other type of 3D representation. Then we have rendering. Most commonly used rendering engine uses rasterization because it's really fast, and the GPUs were designed to do all of this in hardware. But there's volume raycasting, ray tracing, sphere tracing, many other techniques. Even if you think about volume rendering as employed by NERF and other methods, these are all invented in the graphics community in the 80s and 90s. We use them out of the box today. And at the end of the day, you get a single image or multi-view image out. So really what we've done over the last few years in the computer vision community and in this neural graphics community is to make all of this differentiable. And this is really nice and powerful because we can now use images and differentiate back into the 3D representation to optimize a neural field or neural radiance field or some other 3D representation from just images. And then we can do things like view interpolation and maybe extrapolation. I think the extrapolation part is the more interesting part because you can only do it with generative models typically. All right, preaching to the choir, I don't need to convince you that neural scene representations, rendering, and generation is interesting for many different applications. I just want to dive into the generation part a little bit more. So many of you, and I'm going to talk about GANs mostly, not diffusion models, because even though diffusion models are really, really interesting, I think the results that we've seen so far from GANs are still much higher quality, approaching photorealism than the diffusion models we've seen. They're also very fast. So the idea is the following. For a 2D GAN is you take a random noise vector, like sampled from a Gaussian, for example, Z, goes through a generator network, like a CNN, and out comes an image. So what the generator does is it transforms one distribution into another. And ideally, the output distribution is that looks like a natural image. So we need to train the generator, and that's typically done with a discriminator. The discriminator tells you if an image that's generated by the generator is real or fake. And it does that by comparing the fake images, the generated fake images, to some distribution of real data that we have, like a data set. So conceptually, this is very simple, but it doesn't necessarily scale to 3D. So the key challenge, I would say, from a representation point of view is how do you make this tractable? Because you can naively use a 3D generator network, for example, using a 3D CNN, but that's really inefficient and it's really slow. You get like some voxelized representation. And if you want to use a 3D discriminator, how are you going to use these natural images? as a data set to train on. It's just not possible. You need a collection of shapes or something like that, or some 3D representation. And as you probably know, the collections of data sets that we have for 3D is probably ShapeNet and things like that. And those objects are just not realistic enough. So, it's not only computationally inefficient, but even if we're successful, we're going to be able to generate ShapeNet objects, which just isn't that exciting. Okay, so what can we do? Well, let's take a look at the training data that's online now. There's a couple of studio captured multi-view data sets. And I'm just listing Triplganger, for example, here, but there are others coming up. People mentioned, Matthias Niesner's work and so on, and that'll be super helpful. But the problem with studio captured multi-view data is that we're going to have very few identities, and that's not going to change anytime soon, because it's really expensive and difficult to build these rigs, calibrate them, and then capture a lot of different people. Even if you take everybody down the hall and inside your building and digitize them, you're still going to be limited by the number of identities. So we can use synthetic data. There's, I think, NVIDIA released a data set just last year or earlier this year. That Microsoft has this data set. You can generate an infinite number of identities using synthetic data, and you get a lot of diversity, which is great. But the data is not photorealistic, so doesn't serve the purpose either. All these 2D GANs are trained, at least for faces, on data sets like FFHQ. That's a data set of images scraped from the internet with lots of different identities, 70,000 in this case. And there's a lot of diversity in there. So wouldn't it be nice if we could just train our 3D generative model on this unstructured single view data set? Well, that's one challenge. Like, how do you actually train something that is 3D multi-view consistent on this unstructured data? So I'll talk about this next, but there's another thing, is the efficiency. So I don't want to be confusing, but hopefully I can make this clear. I want to give you a sense of how challenging it is to train a generative model. So many of you know NERF, and you can take a pre-trained NERF and render an image. So back when we worked on this, like a year or two ago, rendering NERF was slow. It takes, well, a little while, maybe a couple of seconds or a minute to just render one image if you already have the NERF. Well, training a NERF, at least pre-instant NGP, took a long time. It takes hours or maybe a day, because you have to render so many times. You have to render like 1,000 times. I'm just making this up, but on the order of 1,000 times, because you have to project into all your different views many times, backpropagate the error, update your model, do the same thing again. So you're going to render thousands of times. So it's going to be 1,000 times slower than the inference pass. So now thinking about GAN training takes a long time, because you're going to have 70,000 images in your data set, and you're going to want to do many epochs over the whole data set. So we're talking about, tens of millions of rendering passes before the GAN is trained. And that doesn't even include all your time that you're going to sit there and tune the hyperparameters. So it's going to take a week or so to train this model if it's really efficient, but using conventional NERF techniques, it's just not efficient. So it's going to take an infinite amount of time. So it's just not feasible. So efficiency is really the key to training GANs. You can be clever, but efficiency is the key. And that's going to give you the results. So let me show you how we approach this 3D aware GAN training. So we want to, generate a scene. And first of all, we want to get rid of the 3D discriminator. So instead of discriminating in 3D, we just render some images from the 3D scene and send these images through a 2D discriminator. I mean, that's not rocket science. That's pretty straightforward, but it does make sense. And, people hadn't necessarily done it. I mean, we did it with PyGAN also the year before, but I don't want to talk about this too much. So using a 2D discriminator is key. And the other thing is, a lot of smart people have spent a lot of time doing architecture search on these 2D discriminators already. So ideally, we just use one of them, like StyleGAN, because it works really well. And Taro and others have spent a huge amount of time, doing this architecture search for us. So it's nice to be able to tap into that. Now, one thing that I want to bring back is this idea of the graphics pipeline, this differentiable graphics pipeline. This is actually a key component of a 3D aware GAN, because the graphics pipeline, or differentiable graphics pipeline, goes between the generator and the discriminator and represents a bottleneck. It's a physically based bottleneck that makes sure that whatever the generator actually generates needs to go through the graphics pipeline and then is being rendered, and that's being discriminated. So if you think about this bottleneck, it actually is very useful, because then you force the generator to generate something that's physically meaningful and interpretable, editable, and so on and so forth. So we're just going to take this graphics pipeline and put it in between the generator and the discriminator. So now I'll tell you how we can also change the generator to be really efficient. We came up with this idea. I mean, it's inspired by others that have done similar, variants of this idea, but I think we formulated it and demonstrated to work in a generative setting. The first time we call it a triplane representation. It's stupidly simple. It's basically just 3 planes that are axis aligned, and features live on these planes. So you can query a point in 3D by simply projecting it onto these planes using orthogonal projections, doing a bilinear interpolation on the planes to get the features, and then you're going to aggregate those features. So we used the simplest aggregation function that you could come up with, which is just a sum. You could do a product. Product would be something like a rank 1 tensor representation, right? So for those of you who are familiar with low rank tensor factorization, if you take a 3D volume, you present it as the outer product of 3 planes. That's a low rank or rank 1 tensor factorization. We tried that too, worked well too, but the sum was just simpler and just did the job for us. We're going to aggregate these features, but then the difference between low rank tensor factorization is that we have this really small MLP, just 2 layers of a fully connected network that translate the features into density and color. And that makes it nonlinear. I mean, the product would make it nonlinear too, but this adds a little bit more degree of freedom. So the key idea is to move away from this NeRF representation that has a really large MLP, because it's very slow to evaluate. We need to evaluate it many times, to something that's just really efficient and fast. So the nice thing about this triplane representation is that it's really memory efficient. So if you compare it to a full voxel representation, it just scales quadratically with the volume resolution instead of cubically, which is what a dense volume representation would do. It is amenable to generalization, which I'll show you later. It's really fast to render. And probably the most important thing for a generative setting is that it's fully compatible with 2D generator architectures like StyleGAN. We can just generate all of the planes as image channels, and we don't need to do anything special. We can, again, tap into the vast amount of work that people have already done in 2D GANs and just plug them in here. But before I get there, I just want to convince you that a triplane-based representation of a radiance field is actually a good idea and has enough capacity to represent it, because it seems like you're losing a lot. So we did the single scene overfitting experiment, where we just take a scene from Tanks and Temples and fit, well, back then MIP-NeRF and our triplane representation to the scene. And what you can see is that it looks really good. In fact, the triplane representation is actually giving you sharper text in this case. That being said, triplanes, at least the way we use them in this 3D GAN setting, didn't support view-dependent effects. So the PSNR is still a little bit lower, and a lot of the shiny specularities on the statue aren't captured. But it's faster. It's like at least 8 times faster, or about 8 times faster than MIP-NeRF. And that's the key again. So now, I don't want to bore you with lots of architecture drawings, but the key insight is that we just use the StyleGAN to generate almost out of the box, so with minor modifications. And instead of generating a 3-channel image that has RGB values, we're going to generate an image with 96 channels. These 96 channels are not colors, they're features, and 96 divided by 3, so 32. We're going to chop them up into 3 blocks and rearrange them in 3D. So that gives us a really simple way of doing something in 3D. We then use this feature aggregation, the triplane decoder that I mentioned, and standard volume rendering to render an image from them in 3D. It's still not efficient enough, even though it's pretty efficient. So this raw rendered image is at a resolution of something like 128 square. To get to higher resolutions, we use a 2D CNN upsampler. It's not ideal because it introduces a little bit of the view inconsistencies, but it still gives you higher resolution. So maybe that's okay. Again, this is the neural rendering part. We use the StyleGAN discriminator out of the box. There's the CNN-based upsampler, and so on. Let me show you some results. This is a person that doesn't exist. She looks, I would say, close to photorealistic, not quite yet. You can see some aliasing maybe in the earrings and others, but it looks good. The hair is good. The geometry looks pretty good. We never supervised any geometry. The network just learns to, generate shapes that are approximately correct. They're not fully correct. You see these hollow eyes, for example. That's like that's a bias in the data set, because all the people in this data set look at the camera, and to reproduce that, that means they always have to look at the camera. Anyways, I can go into that in more depth later, but the shapes look pretty good. You get glasses, you get hair, you get all this stuff. We didn't disentangle the background, so the background's still sort of attached to the head. You get a lot of diversity, works on cats, works on other objects. It's close to photorealistic. The FID numbers are actually on the order of like 4 point something, so it gets very close to the quality and diversity of 2D GANs. Not exactly the same. There's still a small gap, I would say, but it's fairly close. Any GAN paper needs to show latent code interpolation. We just basically pick random latent code vectors Z and interpolate between them linearly in this latent space. And what you can see is that the latent space is really good. Any point in this latent space gives you a reasonably looking face, right? So it's a great latent space. And the shapes also interpolate well. Again, there was never any supervision on these shapes. So it's surprising that they actually work so well. Again, there's some ambiguities like high frequency detail around the lips, perhaps, and in the eyes. But other than that, looks really good. The rendering works in real time. We were able to do this at 30 frames per second. You can see that here. This is our interactive viewer, where we interpolate the latent codes of the cats, change the viewpoint. And again, the key message is that to train a GAN or any generative model, you can be clever as you want, and it's not going to work well unless it's really fast. Sometimes it's better to be faster than to be clever, because you have to do so many epochs over the data set. That's really where the power of the generative model comes from. Okay, you can do things like GAN inversion. So given a single image of a person that the network has never seen before, we can now find the latent code vector that best matches this one observation. And then, to some extent, we can change the camera perspective. It's got to be sort of close to the original camera. Otherwise, it degrades a little bit, but it works pretty well. So a pre-trained 3D GAN can be used as a prior for solving inverse problems, basically. What about human bodies? So we've shown faces. Faces are great, but ideally we'd like to get full bodies. Bodies are hard. They're more challenging than faces, actually, because faces are sort of all the same. I mean, we all look different, but we all have a head, we have 2 eyes, we have a nose, we have a mouth, and they're approximately at the same position. So if the data is pretty well aligned, that works well. For bodies, that's not necessarily the case. If we have, we all have bodies, we all have 2 arms and legs, but in any one photo, the arms and legs will be in different poses. The body poses are so drastically different across different photos that it's going to be challenging to have this alignment. Also, there's going to be lots of accessories and other things. So it's actually a lot harder to train these bodies. In order to tackle this problem, we came up with an idea where we generated the body, or like a triplane representation of the body, in a canonical space where they're all aligned. Makes it really easy. And then we have a non-rigid deformation field on there that just deforms the canonical body from the canonical space into this, into the body pose distribution of the data set. And back then we used AIST++, so the data was sort of not as diverse as FFHQ, for example. But it worked okay. The method worked okay. The quality is sort of limited still, mainly by the data set. But we generate these different identities in this canonical pose, and then we can drive them to arbitrary poses using, for example, a skeleton or a simple mesh that's articulated. And that was interesting. So that was NeurIPS last year. We call this Generative. But we can generate these different identities for bodies too. But again, getting good quality for bodies is much harder than for faces, because you have so few pixels, even for the face, for example, here. And yeah, the upsampling network is going to make it a little bit view inconsistent and so on and so forth. The training data wasn't good back then. So this is still an open problem, I would say. More recently, we've been looking at, putting more and more of this physical bottleneck in there. So instead of generating colors, we can also generate diffuse albedo, specular terms, visibility functions, things that can be used for physically based lighting model. So if you do the lighting actually explicitly, that's nice because you can actually change the environment map after the fact and relight the characters. And that's great because you get more and more control and editability over these generated characters in 3D also. So here's the latent code interpolation of the same identities that are changing with different environment maps. That's nice because if you want to generate assets, it'd be nice to be able to relight them. Or if you want to do things like solve inverse problems where you take a picture of yourself and you want to change the lighting after the fact, you can do that with a pre-trained model like this. Okay, sort of running out of time, so I'm just going to give you a quick outlook of some interesting things that you can see at CVPR and beyond right now. We use this triplane representation also for what would traditionally be considered a 3D reconstruction task. And this actually goes back to a really good point that Andrea was just making in his talk, is like, let's think about this in a Bayesian framework. So given a couple of images of a scene, typically we think about 3D reconstruction as a maximum likelihood or map problem, where we minimize the negative log likelihood of, you know, the 3D scene that minimizes the negative log likelihood of these observations that we have. And so there's, you know, one reconstruction given the set of images, and that works really well. But if we think about this as a generative problem, then we could say, hey, what is the distribution of 3D spaces that all map into projections that match our observations? And if you do that, you get something like what we call scene graph, generating diverse 3D scenes from the same input. You actually generate a distribution from just the same observations of plausible 3D spaces that could all have resulted in these observations. So if you're interested in this, go find Mingjung at her poster at CVPR this week, and she can tell you more about it. You can now do things like generate these 3D scenes, change the camera perspectives, and even do things like latent code interpolation, which is really uncanny because you're sort of warping these 3D scenes from one to another. So it changes the layout in 3D, which is interesting. And it even works on real data. So again, I don't want to spend too much time on this. If you're interested, go see the poster. It's going to be presented this week. We also started looking into diffusion models like everybody else, of course, too. And our first approach was to use triplane representation and use a diffusion model on the triplane. So again, we can use a 2D diffusion model to diffuse 3D shapes. And that worked really well. You can see this also, it's a paper called 3D Neural Field Generation using Triplane Diffusion. You can see that at CVPR this year. And Ryan, who was a high school student at the time, doing an internship with me, actually coded this up from scratch. So you can do this too. It's really simple to do and works pretty well. One other thing that we've been looking at in terms of diffusion models is to not only generate individual objects, but starting to look at compositional scenes. So you can do things like put bounding boxes into the scene, use text conditioning on each of the bounding boxes, and then use the diffusion model to create a really nice compositional scene. So it's very different from composing 3D objects together after the fact, because we can get shadows, reflections, things like that, if the score distillation loss is applied on the generated composed image. So this is something that's on arXiv and really interesting. Finally, we've been also looking at these single view condition problems where you have a single image and you want to do view extrapolation from a single image using 3D diffusion models. So we approach this by taking the image, extracting features, lifting them in 3D, projecting those features into different views, and then applying a 2D diffusion model onto those projected features. Works really well too. We're inspired also by Andrea's work. So here's the input view from a single image of real data. You can get pretty good results with ViewFormer. I think that was from Andrea's group also. But approaches like PixelNerve that use an L2 loss, they're going to be always really blurry because they give you the maximum likelihood solution, which is going to be an average of all the plausible solutions. Whereas a generative model, like we called ours GenVS, will sample from the posterior distribution of all the potential solutions for this view extrapolation problem. So this is really interesting, and also real data, which works on. So here's a single view of an indoor scene. You can do things like look outside the room. It works okay, but GenVS actually generates plausible long trajectories of these indoor scenes of real data. They're not exactly real because it's a generative model. It doesn't reconstruct the scene. It generates something that's plausible and 3D multiview consistent. So take a look at GenVS if you're interested in this. Few key takeaway messages is that, I concur with what Andrea said earlier. We want to do, the best of AI and 3D, so 3D structure. So we want to combine physics and learning in a meaningful way. That's really the key. Adversarial training is great. It allows us to learn 3D multiview consistent data from unstructured single view data sets. So ideally, we don't need to work with multi-view data that's limited or synthetic data. Triplane representations are great. They're just so simple and fast that they're very versatile. Okay, that's it. Thanks to my students, especially Eric and others here for doing all the work.
Thank you, Gordon. Okay, so we have a few minutes for questions, and as long as I just realized earlier that I didn't turn on my camera. Can you see me?
I can see you.
Great. Yeah. So while others think about questions, I'm going to ask one that I'm going to also ask the other panelists later. But unfortunately, as you can't be on the panel, what do you think? Okay, so we can generate really nice assets. We can generate assets in 3D, in 2D. That's fantastic. We've seen Björn Ommer's work on generating, images, text using text input. But how can this be useful to understand the world, to do like AI, so really understanding images? So is there like a way of doing like inverse rendering? I mean, you're showing that you can reconstruct images, but is there a way of understanding the world through these generative models?
Perhaps I would say this is actually AI in the sense that we don't do single scene overfitting where we fit one nerve to one set of scenes. Typically, we actually learn the distribution of objects. Most of these GANs work well in an object-centric space, not so much for complicated compositional scenes, right? Can we learn something about this distribution of objects? I think we can, but we need to dive into this latent space that's actually being learned, or into the weight space. And I think we did some work earlier on analyzing the space in the sense that we use this I think about this as a fully unsupervised training stage where you learn the latent space, and the latent space actually does learn a lot of structure. It's just not supervised. So one thing we did in a work with Vincent a couple of years ago was actually to do a few shot supervised learning with classification. And it worked really well to understand the different parts of the object. So the knowledge is in there, but I think it requires a little bit of, semi-supervised training of this data with little data. That's sort of how these large language models are also trained, is you take all the data you can get in the internet, you do an unsupervised pre-training stage, and then you have a much smaller amount of labeled data that you use to now do this semi-supervised approach to actually tell the object, oh yeah, you've already learned how to cluster different parts of the body. Now I'm going to tell you that this is an arm and this is an ear, because you didn't know that because I never told you what that is, right? That's sort of how kids learn too. I mean, I have two small kids and they run around the world and they get a lot of observations, but I do need to tell them what's what. I need to tell them that this is a nose, and then they will know, oh, I've seen this thing before many times. I've seen this. Now I'm going to attach this name to it, right?
Got it. So if I understand you correctly, you could imagine actually robots using these kinds of generative models and then learning in a weekly semi-supervised few-shot manner?
Absolutely. Yes.
Cool. Questions?
Thank you. So I have a question regarding like raising the generative models for 4D scenes. Like right now, a lot of the work has been on static scenes only. So do you think if you like raise it to like a 4D, would it be similar incorporating generative models?
Oh, great question. First of all, I would say the answer is nuanced. It depends on what 4D type stuff you want to do. I would say with our work on Generative, we generated articulable 3D assets, and they're sort of 4D because you can manually change them and articulate them, so they're animatable. So that's interesting. But if you want to learn videos, first of all, you need a 2D video data set, and there's a lot of video data on YouTube, but there's all sort of low resolution and not that great. So if we had good training data, I think you can do it. And then the triplane representation actually extends to arbitrary dimensions. It's basically go back to these ideas of tensor factorization. Now you're going to factor a 4D tensor instead of a 3D tensor, and there are different ways of doing it. You could do 2D planes in each combination of 2 dimensions. That ends up being something that I think Sarah Fridovich-Kyle from Berkeley called K-planes. So you could try to learn that, but you can also use the outer product of just vectors, for example, and think about this. There are many different ways of factoring a 4D volume, and they're all very efficient. So I think the idea extends to 4D generation, but I haven't tried it. So this is a really great direction for future work.
Sorry, as a follow-up, like for simple 4D with like a time as an actual dimension, you can kind of simply raise triplane to like a 4-plane representation. But if you kind of condition on, for example, like human poses, so articulable like human model, a human motion generalization, or like face generalization, you kind of condition on some other kind of like arbitrary number of dimensions. So do you think it is possible to actually raise it to kind of 50 dimensions for the triplanes for more efficient representation, or anything else would be possible?
Well, I think you have to just be, yeah, so the articulable part is I think pretty well defined. Like we did it for faces and for bodies in GNARF, and there have been a couple of follow-up works that got really nice bodies, like human GAN is a data set that just came out a couple months ago, and a few methods have trained articulable characters on this human GAN data set, and the data set is really nice. So all of a sudden the results are much nicer. They're still not the same quality as, let's say, EG3D for faces, but it's getting there. So that works. And yes, you're right. We can extend the concept of a factored tensor representation to 4D if you have object classes that are not articulable. Like you need a skeleton or some kind of a template mesh if you want to do that. So faces and bodies work, maybe some types of animals. But if you want to do vases or how they break when they fall, I mean, there's no articulatable model for that. So you can, I think tensor factorization extends to higher dimensions, and there are many different ways to factor a tensor, as I mentioned. And ping me on email if you want to chat about this more. But you can use 1D vectors to span a high dimensional space very efficiently. How expressive that is a different question. And then I think the higher dimensional you get, you know, the more clever you have to be in terms of like feature aggregation, representation, and so on. But you could do, the easiest thing to do is you take a triplane representation and an additional 1D line that represents time, and you just use the outer product of that.
I see, thank you. That's very insightful.
Okay, then for the sake of time, I think we have to stop here such that we get the panel discussion squeezed in before the lunch. Thanks a lot, Gordon, for making this possible and for being here live. And
thanks for having me.
Thanks.
Bye-bye.
Bye. Okay, so we are going to stop the Zoom now because we unfortunately cannot stream it live, the panel discussion. So that's unfortunate that you're missing out on this, but we'll be back online in the Zoom after the lunch break at 1:45 p.m. Thanks a lot for everyone being online. We had like around 70 to 80 visitors online. That's fantastic. Thanks, everyone. See you later. And we are going to set up the panel discussion now.